Welcome back to another Regents Physics review. This will be for the waves portion of the 2022 June exam, both the multiple choice and the free response questions. So let's get into our first example. All right, so example number 1, where a person standing on a sidewalk hears the siren of an ambulance as it approaches, passes by, and goes away from the person. Compared to the frequency of the sound emitted by the siren, the frequency of the sound observed by the person during this event is, and your answer choices are higher only, lower only, first higher then lower, and then first lower then higher. So with this, it's good to draw a diagram out to figure out what's actually happening. This is a classic example of the Doppler effect. So what I'm going to do here is show what happens to the sound waves as the ambulance goes by with the observer here. So let's look at this with our ambulance. So we're just going to make a box. And the sound waves surrounded it. So as an object is moving, let's say it's moving to the right here, at the front of its forward motion, you're going to have the sound waves become compressed. So I'm going to show this with circles. And at the back of its motion, the sound waves are going to spread out more. So you can see here how I have them closer together at the front and a little bit more spread out at the back, and I'll put in one more here just for good measure. All right, so that's my ambulance there, and the sound waves are surrounding it. I'm going to put the person here at the front of the ambulance and then the person at the back of the ambulance to show the difference between the two. So we can kind of look at this based on our wave speed equation, because that's going to give us a relationship between frequency and wavelength based on a moving object. So for sound waves here, we have V equals F lambda. So at the very front here where you have the person, so I'm going to circle this in red. So our first situation here, we have when the ambulance is moving towards my person on the sidewalk. You can see here that my wavelength is much shorter, so my wavelength, say, is lower. Since my velocity for sound in STP would be 331 meters per second, velocity of sound is going to be a constant. We have to then have, if my wavelength is lower, my frequency then must be higher in order to keep my velocity constant. So that's going to be my first situation here with the ambulance coming towards the person. So I should have higher here. So I can get rid of answer choices 2 and answer choice 4 because both of those say that I will have a lower pitch at first or a lower frequency. Then the ambulance is going to move past me, and I'm going to be in this situation here, so I'll make this green around it. I'm going to be over here. So as the ambulance moves past, the wavelength gets larger and larger. So looking again at my wave speed equation, V equals F lambda, my velocity is going to be a constant. So now if my wavelength is going to increase, my frequency then must decrease. So I will have here first higher for my red portion, and then it's going to be lower as it goes past. So the only answer choice that shows that is going to occur is answer choice 3. So answer choice 1, that's not enough because it's not only higher only, it's going to get lower as it goes past me, so that's why that is no good. So answer choice 3 is going to be my best answer. First higher, since I have lower wavelength at the front, so my frequency must increase. Then as the wavelength spreads out at the back of the ambulance, I'm going to have a lower frequency in order to combat the higher wavelength. So it's answer choice 3. So let's move into our next example. All right, so example number 2, we have which phenomenon represents a wave spreading out behind the barrier as the wave passes by the edge of the barrier. So we have here answer choice 1 is diffraction, 2 refraction, 3 reflection, and then 4 interference. So let's draw out what each of these things are, and then we can figure out which one it's going to end up being. So diffraction, that is a situation where, say I have a barrier here. So say I have this small barrier, and there is going to be an opening in between the two barriers, and I have wavelets moving through to this opening. And as they go past, they will end up bending as they move through. So that kind of shows what they're asking me in the question, but I'm going to write out all of these because it's just good practice. This is answer choice 1. So answer choice 2, I have refraction. And refraction is going to be when light bends going from one medium to another. So say here I have whatever this is going to be. I have a light wave moving this way. As it goes into the other barrier, is then going to say it's going to bend towards the normal line here, so it will actually then slow down, meaning that my wavelength will also decrease. So I have here, I'm going to try and show that to the best of my ability. So it's going to bend from one medium to another. This is not saying that I'm going from one medium to another, so refraction is not going to be the answer there. 3 here is reflection. So that's just when the wave is going to bounce off something else. So say if you have a light ray or a laser on a mirror, it's going to bounce off the mirror. So similar, like looking diagram at first to reflection, it's just then going to bounce off in this direction. And then number 4 is interference. That is when you have, say, a crest and a trough moving together, or a crest and a crest. So say I have here, say I have 2 crests moving together. At this point here, I would have constructive interference. Or if I had a crest and a trough, I would have destructive interference. So which answer is this going to be? It says that the wave is spreading out behind the barrier as the wave passes by the edge of the barrier. It's going to be diffraction, answer choice 1 here, because as it goes by the barrier, it's going to spread out or bend around the barrier. That's what's being described in this situation here. So answer choice 1 is going to be my answer. So let's move in to my next example. All right, so example number 3. We have an acoustic organ is a musical instrument with pipes. The oscillation of air molecules in the pipes of the organ produces sound waves that are answer choice 1, electromagnetic and longitudinal. Answer choice 2, electromagnetic and transverse. Answer choice 3, mechanical and longitudinal. Answer choice 4, mechanical and transverse. So the difference between mechanical and electromagnetic waves: electromagnetic is anything that is going to be light. Mechanical is kind of what it sounds like, something that can be made by man. So think about like a rope would be an example of a mechanical wave if you put it back and forth. The springs would be an example of a mechanical wave if you shook it back and forth. A wave in the ocean would be an example of a mechanical wave, and of course this one, a musical instrument, would also be a great example. A sound wave would be a great example of a mechanical wave. Versus electromagnetic, that is really anything on the electromagnetic spectrum. It is just light, even if we cannot see it. So since this is a musical instrument, it is not light, it is going to be sound, so it's going to be a mechanical wave. So answer choice 1 and 2 can go away straight away, and it's just knowing your vocabulary between longitudinal and transverse. So transverse is going to be the up and down wave motion, and then longitudinal is the side to side, or it's parallel, say, to the propagation or the movement of the wave. For your longitudinal wave, that is going to be for sound waves because it moves the air back and forth as I speak into the mic right now, and then that sound goes to your eardrum. That is going to vibrate the air molecules back and forth and then vibrate your eardrum as well. That's what's creating the sound. Is going to be a longitudinal wave, not a transverse wave. So if it is sound again, sound is longitudinal, and it is mechanical. That's really what you have to get out of this question. So answer choice 3, mechanical and longitudinal, is going to be your answer. So let's move into example number 4. So example number 4. Which list identifies portions of the electromagnetic spectrum in order of increasing frequency? All right, so whenever you get a question like this, and it specifically is going to say here electromagnetic spectrum, all you're going to do is go to the reference table, go to page 2, and look at the electromagnetic spectrum and try and line it up with the list that they're giving you. So for frequency on electromagnetic spectrum, it goes right to left. So the leftmost part of the table is going to be the greatest frequency. The rightmost part of the table is going to be the least frequency. And it also tells you on here for like future things, if you're looking for a question on part 2 where it tells you to find something in frequency, it does give you the units for it here as hertz, your abbreviation from hertz down to Hz. So what you'll do now is just look at the answer choices and see which one is going to be correct based on what they give you. So answer choice 1 says that we have gamma ray first. There's a problem with having gamma ray first since we're going to have an order of increasing frequency. If you look at the electromagnetic spectrum, and again going from right to left is my increasing frequency, gamma rays are the leftmost on the entire table, meaning they have the greatest frequency. So I can't go above that. So if gamma ray starts off my list, that means I can't go and increase in frequency at all. Everything has to be below it. So this answer cannot be correct. So answer choice 1 is not a correct answer, and answer choice 4 can also not be a correct answer because any of the electromagnetic spectrum on the list after that is going to be below the gamma ray in frequency. So 1 and 4 cannot be correct. So look at answer choice 2 now. We have ultraviolet, it starts off with. So we're starting off with ultraviolet. We then go to visible, which is to the right of ultraviolet, which again, that means we are decreasing in frequency, not increasing in frequency. So this answer is also going to be incorrect. Also, you go then to infrared, which is also decreasing in frequency. So this answer will also be wrong. So by process of elimination, you're going to have answer choice 3, but let's just make sure that it's correct here. So you start off here with infrared. Of course, you now want to go left on the table to get increase in frequency. So you start off with infrared, you go to visible light, that is to the left, so it has a greater frequency. Then you have ultraviolet, that is also to the left, so that has a greater frequency. And then finally, the gamma ray, that is the leftmost on the table, so that is also increasing in frequency. So answer choice 3 is going to be my answer. So let's move on to example number 5. All right, so example number 5, we have a tuning fork is used to produce a sound wave having a frequency of 512 hertz. What is the wavelength of the sound wave in air at STP? All right, so this is a math question. So with the math questions, you always want to take out what they give you in the question, write it out on the side, and then figure out an equation you're going to have based on that. So we have here, the first thing that I have is a frequency of 512 hertz. So if I don't know what frequency is on the reference table, I can look around for it. As far as equations go, it is going to end up in waves. And I can see that frequency is F. So I have here that F is going to be equal to 512 hertz. All right, next thing here is what is the wavelength of the sound wave in air at STP. So it seems like, or seemingly, it only gives us one number in the question because it's asking us to find the wavelength. And again, if I don't know what a wavelength is, I go to the reference table, I see that it's just Greek letter that's kind of like upside down Y, which is called lambda. This is what I'm looking for, so this is my question mark. And then it says a sound wave in the air at STP. If I don't know what that means, I look around the reference table for it, And on the front page, there are a bunch of constants. On here, it says that we have the speed of sound in air at STP. That is going to help us if I want to find the wavelength, because the equation that can help us find the wavelength, that is the velocity, v, which is the speed of sound in air at STP, which is 3.31 times 10 to the second, or 331 meters per second. There is an equation that involves all three of these variables that can give us the wavelength of sound, or of a sound wave in this situation. So we have here v, f, and lambda. The equation is v equals frequency times wavelength, written out as so. So v equals the frequency times the wavelength of the wave. So again, what I've been doing with this, I'm going to solve for the wavelength first and then plug in the numbers, acting like it's a part 2 question, since that is good practice. I have here v equals frequency times the wavelength. I want to get wavelength by itself, since that's what I'm solving for. It's currently attached to the frequency by multiplication. So I'm going to do the opposite of that and divide out the frequency from both sides of the equation. And I should end up with v over f equals my wavelength. So now I can just plug everything into the equation and end up with my answer. So my velocity is 331 meters per second. My frequency is 512 hertz. That is equal to my wavelength. All I'm going to do now is plug this into my calculator and get my answer. So 331 divided by 512. And I'm going to end up with my answer as 0.646 meters equals my wavelength. And that's going to work out for my units, because hertz is essentially 1 over seconds. So the seconds will cancel, and I'll have meters left. So that's why my unit there is meters for wavelength. So my answer choice is answer choice 1, 0.646 meters. So let's move into my next example. All right, so example number 6. We have an amplified sound wave produced by an opera singer shatters a glass. Which phenomena best explains this event? All right, so we did this in class. We showed a video of the speaker that broke the wine glass, and we explained what it is. So whenever you have a sound that is going at the same frequency as, say, the natural frequency of an object, in this situation is a glass, it causes the glass to vibrate at that natural frequency, which is called resonance. So that's just really knowing your vocabulary there, that resonance is that vibration when you bring a sound that has the same frequency near something that has that natural frequency. So that's why you see where they try and break a glass, they tap the glass beforehand to get the natural frequency, and then usually they'll use a speaker in order to do it, unless they have perfect pitch. They use that speaker. They have the speaker at the frequency that they heard with when they tapped on the glass, and then they're able to get the glass to move at that natural frequency until it eventually breaks. So that is called resonance. So answer choice 4, resonance is the answer. So let's move into our next example. So example number 7. We have in medium X, light with a wavelength of 3.44 times 10 to the negative 7th meter travels at 2.2 times 10 to the 8th meters per second. In medium Y, this light has a wavelength of 3.12 times 10 to the negative 7th meter. What is the speed of light in medium Y? All right, so another math question. So let's look at what we have in the question and then figure out which equation we're going to use based on that. So the first that I see here is that I have a wavelength of 3.44 times 10 to the negative 7th meter. So I can put here wavelength equals 3.44 times 10 to the negative 7th meter. It then says that this light is going to travel at 2.2 times 10 to the 8th meters per second. That is going to be my velocity v. So we have here 2.2 times 10 to the 8th meters per second. Then we have in medium y, it has a wavelength of 3.12 times 10 to the negative 7th meter. So that gives us a second wavelength. So I'm going to make this wavelength up here, wavelength 1. This will be wavelength 2. And again, for wavelength, if you forget what it looks like, on the reference table, you have wavelength is equal to lambda on there. So wavelength 2, this gives it to us as 3.12 times 10 to the negative 7th meter. Then finally, we're trying to find the speed of this light in medium y. Since we're trying to find the speed, we'll make the first one v1, we'll make this v2, and that's a question mark. All right, so looking at an equation that involves two velocities and two wavelengths. Since we're working with waves, we should be in the waves portion of the reference table. Also, it's telling you wavelength, so that's how it tips you off to be in the waves portion of the reference table. And look for an equation that involves two different velocities and two different wavelengths. Look at the very bottom of waves. I have an equation that is n2 over n1 equals v1 over v2, which equals wavelength 1 over wavelength 2. That's the equation we're going to use. We're going to use the last portion of it here, which is v1 over v2 equals wavelength 1 over wavelength 2. So again, I'm going to solve for this algebraically. I want to get v2 by itself on one side first and then plug it in the numbers, so it'll make my life a little bit easier. So since v2 is being divided by v1, I am going to multiply it on both sides first in order to get it on top. So we have here v2 on this side. That will cancel out. And I'll have v2 on the right side. So I should have that v1 is equal to wavelength 1 over wavelength 2 times v2. All right, so wavelength 1 over wavelength 2 is attached to v2. So all I'm going to do is divide that out from both sides. So divide this out here. So over here, it will cancel. On the other side, it will essentially be flipped here. So when I do this, since like the ends multiply to each other and the outers then go to the outers also multiply to each other here, what I'm going to have here is wavelength is going to go to the top, so wavelength 2 times v1 over wavelength 1 is going to equal v2. So now I can plug everything in and end up with my answer. So I have here wavelength 2, that is 3.12 times 10 to the negative 7th meter. That is then going to be multiplied by my v1, which is 2.2 times 10 to the 8th meters per second. That is all over my wavelength 1, which is going to be 3.44 times 10 to the negative 7th as well. That is meters. This is equal to v2. All right, so plug this into my calculator here. 3.12 times 10 to the negative 7th multiplied by 2.2 times 10 to the 8th. That should give me 68.64, and that's going to be meters squared per second. That is then all over 3.44 times 10 to the negative 7th meter. That's equal to v2. So v2 is going to go over here when I get the answer. So then divide these two. So 68.64 meters squared over seconds divided by 3.44 times 10 to the negative 7th is going to give me an answer of, so let me erase this so I have a little bit more room. So V2 is going to be equal to, rounded off, 2.0 times 10 to the 8th meters per second. So this should end up with 199,534,883. With that, that ends up becoming 2.0 times 10 to the 8th meters per second. If you don't want to do scientific notation from that, you can do in your calculator. You can change the mode to science. Then you could go do the answer again, and you will end up with 2.0 times 10 to the 8th. That is going to be my answer for velocity 2, which is answer choice 1 here. All right, so let's move into our next example. All right, so example number 8. The diagram below represents a wave traveling in a rope in the directions indicated. So it shows that the wave is traveling to the right. So which arrow represents the motion of particle P at the instant shown? So what I'm going to do with this is essentially draw the wave just like a moment later to show where point P would end up being. So I'm going to start off over here and just draw the wave here. So drawing the wave. All right, so that's just showing that the wave, like just a moment later, where point P would be. So essentially, point P is going to ride the wave since the wave is going to the right, and these particles can only move up or down. You're going to see here that point P should now line up with the crest up here of the wave, essentially. So it's going to move upwards. That's kind of the best way in order to do this. Just look at the direction in which the wave is moving and draw the wave like a moment later. So start it a little bit after its original starting point, and you should see where the object is going to move, or where the point is going to then move. It should be up or down for a transverse wave. It's never going to be side to side. So say answer choice 1 and 3 would not be an answer ever for a transverse wave. So you're only looking at 2 and 4. And again, just draw the wave. So if you had it going to the left, you could draw it and it would end up then going downwards if it was going to the left. But since the velocity is to the right, it is going to go upwards. It's essentially just riding that wave up as it moves through. You can also think about it as, say, a ocean wave. If you were standing in one place on a surfboard and the wave was moving towards you, you would then move upwards with the wave. So similar idea with that. So answer choice 4 is going to be the answer. The point moves upwards for this scenario. So let's move into example number 9. So example number 9, we have the graphs below show the displacement of a certain particle in a medium versus time due to two periodic waves, A and B, traveling through the medium. The superposition of the two waves will cause the particle of the medium to have a maximum displacement of. So with this, what does superposition mean? It just means that when the two waves move on top of each other, what's going to happen to the amplitude essentially. So it's not going to be destructive interference because they're both in phase with each other. So we'll have constructive interference. If they were out of phase with each other, you have a difference here. But you can see here how these peaks or crests are going to line up with each other. So are the troughs. So that means that the wave is going to be in phase. So we look here, the superposition of the two waves will cause the particle of the medium to have a maximum displacement of. So what we do is add these together. So in wave A, we have a displacement of 2 meters. In wave B, we have a displacement of 3 meters. So if you just add them together, 3 plus 2, so I'll show here. 3 plus 2 is going to end up being 5. So that is answer choice 4. And again, when you look at the superposition of the waves, is just when they move on top of each other. So if they're in phase, they're going to create constructive interference. If they were out of phase, they create destructive interference. So answer choice 4, 5 meters, because the 3 and the 2 will be your answer here. So let's move into our next example. It's example number 10. We have which graph represents the relationship between the speed of light in a transparent medium and the absolute index of refraction of the medium. So an equation that involves the index of refraction of a medium and the velocity in that medium is going to be this equation. So we have here that n equals c over v. And this really just shows that the index of refraction is the ratio of the speed of light in a vacuum over the speed of light in that medium. So again, the greater the index of refraction is, the lower the speed is going to be in that medium. So when I look at this, you have the index of refraction here. You have the velocity in the transparent medium here. So they are going to be inversely proportional to each other. So the only answer choice that is going to make any sense for this is going to be answer choice 1, because that is the only one that has, as the index of refraction increases, the speed of light is going to decrease. So the rest of these answers are no good. 3 is to confuse you with the speed of light in a vacuum. So that is not going to be correct. So answer choice 1 is the other one that makes sense, because it does correctly show that as the index of refraction increases, the velocity is going to decrease and it will never become 0. So that's why asymptotes here at the bottom. So answer choice 1 is your answer. So let's move into example number 11. So example number 11. We have 4 mechanical waves are created in the same medium over the same time interval. Which diagram represents the wave that transfers the greatest amount of energy? So for a mechanical wave, the energy is going to come from the amplitude of the wave. So that means, like for a sound wave, the louder I am, the more energy I'm going to have, the greater the amplitude of my sound is going to be. So all you're going to look at for this question is which diagram has the greatest amplitude. Again, amplitude is from the equilibrium point, so the 0 here, all the way up to my crest or down to my trough. So for any of these, from 0 to its highest point or its lowest point is going to be the amplitude, not the 0.3 to 0.3. So look at this. The one that shows the greatest amplitude is going to be answer choice 2. That one is the highest. It goes from 0 to 0.3. None of the other answer choices show this. So answer choice 2 is going to be my answer. So let's move into our next example. So example number 12, the final multiple choice one here, with which diagram represents a light ray increasing in speed as it travels from one medium to the other. So with all of these, when you have a light ray that increases speed, it is going to move away from my normal line. If it decreases in speed, it is going to move towards my normal line. So which answer choices are going to show this increase in speed? So let's look at answer choice 1. So we have it from medium B into medium A. This shows here that I have a greater angle of incidence compared to the angle of refraction. This means that I have to actually slow down. So answer choice 1 is not going to be my answer. Same thing for answer choice 2. We have a smaller angle of refraction than we do an angle of incidence. So that means that my light ray is going to slow down from one medium to the other. So this answer is incorrect. Answer choice 3. You have a small angle of incidence, but a fairly large angle of refraction. So that looks like a good answer. And you have answer choice 4, where it seems like the angles are exactly the same. So that means that there was no change in speed. So answer choice 3 is going to be my answer. because I'm moving away from the normal line as I go from one medium to the other, which shows that I've actually sped up, not slowed down. So answer choice 3 again is my answer. So let's move into our free response questions. All right, so example number 13. We have a student produces a wave in a flexible spring stretched along the table by shaking one end of the spring at a frequency of 2.0 hertz. Part A, determine the amplitude of the wave produced in the spring. So that would be 1 point on the Regents. So amplitude. Amplitude is going to be my distance from the equilibrium point of the spring. So we can start off here where the spring or the wave starts to my crest or to my trough. So what I have here, the equilibrium position is going to be my dotted line. That's the equilibrium of the wave. Then I have the crest over here and the trough over here. So distance from this equilibrium point to either my crest or my trough is going to be the amplitude. But I'm not given the equilibrium point here. I'm given the distance, the 1 meter, from my trough to my crest. So what I can also do with this is just take the distance from the trough to the crest that I've been given and divide it by 2. Since I have 1 meter for that total distance from the trough to the crest, I can divide that by 2, and that answer is going to be 0.5 meters, and that's going to be my amplitude. So the amplitude here is going to be 0.5 meters. Again, that's the distance from my equilibrium point, this dotted line here in the middle, to either my crest or to my trough. It's not the total distance here. If I'm using the total distance, which is the 1 meter, I divide that by 2, and that's how I end up with the amplitude here of 0.5 meters. So let's move into part B. So part B, while determining the wavelength of the wave produced in the spring. So there's a few ways to find wavelength. One of them, of course, is using the wave speed equation. If I had the frequency and the speed of the wave, I could do that, but I only have the frequency. So that's not going to help me at this point. So I can go to my other 2 ways of finding the wavelength. One of them is if I had the distance between crest to crest, or trough to trough, or the cycle, the equilibrium position to the beginning of another cycle, the equilibrium position, I could find the wavelength that way. My arrow does not show that. What I have there on the bottom is the total distance of the entire spin or the wave in this situation. So I cannot use the distance between crest to crest or trough to trough or from one cycle to the other. My third way of doing it is when I'm given this total length, I can then figure out the amount of cycles present in the wave and take the total length divided by the amount of cycles and end up with the wavelength that way. That's the way I'm going to do this example here, because that's the only way that will work for this one. Since I have the 4.5 meters, I have here that's the total length, so I can write this down here as length is equal to 4.5 meters. Then my cycles, so I'm going to find my cycles. So the cycle here is going to be from my equilibrium position up to my crest, back down to the equilibrium position, to the trough, and back to the equilibrium position. That's going to be 1 cycle. So I'm going to show that with different colors here. So I'll get rid of the 2 things here at the end. So I'm going to start here with red, showing the first cycle. Then I'll choose another color for the second cycle and whatever the other cycle is going to end up being. So we'll start off here. That's my starting point. I go up to the crest, come back down to the equilibrium position, go down to my trough, and come back to the equilibrium position. That is going to be 1 cycle. So then my next cycle starts here as well. I can go up to my crest, come back down to my equilibrium position, go down to the trough, and come back to the equilibrium position. that is my second cycle. And then my third cycle will start here as well. I will then go up to my crest, come back down to the equilibrium position, go down to my trough, and come back to the equilibrium position, and that is my third cycle. So I have 3 cycles in total. So all I have to do here is divide the length, or have the length divided by the amount of cycles, and I will get my wavelength. So wavelength is going to be length over cycles. So I have here that the wavelength is going to be 4.5 meters over my 3 cycles. Oops, let me fix that 3 again. So 4.5 divided by 3 is going to give me a wavelength of 1.5 meters. So that is going to be my answer for part B, and my answer for part A was 0.5 meters. So let's move into my next example. All right, so example number 14. This one we'll do in a couple different slides because it's a little bit longer than the other examples. I'll show that in the chapters of the video. So we have here the diagram represents the path followed by a ray of light, the frequency of which is 5.09 times 10 to the 14th hertz, as it strikes a semicircular block of fused quartz perpendicular to its curved surface. So part A, use a protractor to determine the angle of incidence of the light ray at point O. So what I've done here is I put a protractor into the diagram to just show my thought process on finding the angle here. So part A, finding the angle here for the angle of incidence. So you have here point O, which is down here, and you have your protractor. So I'm measuring it from the normal line. So the normal line here lines up with 90 almost perfectly. I couldn't get it quite perfect for the diagram here. So we'll just pretty much estimate, but they give us a little bit of leeway with the angle anyways. So looking here at the normal line, which is down the middle here, lines up with the 90 degrees pretty well. And this is my angle of incidence, or my incident ray. So that's going to give us the angle of incidence. So from here, I'm just going from 90 to around 120, and that's going to give me the angle. So if I go to 100, that's 10 degrees. 110, that's 20 degrees. I don't get quite to 120, so I have here, this point here is going to be 5. So I'm at 25 degrees, and I'm just going to count from there. So 1, 2, just about 3. So we're going to be from 25 plus 3, so about 28 degrees for my angle of incidence. So I'm going to call that angle 1, and that is going to be 28 degrees. I believe you have plus or minus 2 for that. So if you're a little bit off, either up or down, you're going to get the proper answer as well as you continue with that angle. That should end up getting you the full credit on the Regents. So part B here, we want to calculate the angle of refraction as the light ray leaves the fused quartz at point O and enters the air. All right, so with this, there's one equation that's going to end up coming to mind, and that's Snell's law, because I have 2 different materials or mediums, and I'm trying to find some angle. So my first medium is going to be the fused quartz, so that's going to be N1. And I'm not given that index of refraction in the question, so if I don't know what that is, I go to the reference table on the second page, and I see I have a table of the absolute indices of refraction. So looking at that, I have the fused quartz towards the bottom is going to be 1.46. Then we just found my angle of incidence, which is going to be the 28 degrees. And then my second indice of refraction, or second index of refraction, is going to be the air. Air is just 1.0, so that is going to be N2. Oops. And then finally, I want to find the angle of refraction, so that's going to be theta 2. That's what I'm looking for. All right, so again, I'm going to solve for this algebraically first and then plug in the numbers because this is a 2-point question. So this is going to get me my first point, and my second point is just going to be the answer. So we have here the equation that involves two indices of refraction and two angles is n1 sine theta 1 equals n2 sine theta 2, and again, this is on the reference table in the waves portion. So I want to get theta 2 by itself because that's what I'm trying to find. The first thing I can do with this is divide out n2 because it is attached to sine theta 2 by multiplication. So doing the opposite of that, should now have n1 sine theta 1 over n2 is going to be equal to sine theta 2. Whenever I need to get an angle and it's attached to sine, I'm going to do what's called arc sine. Essentially, that comes from sine is attached to theta 2 by multiplication. I can divide it out from both sides. And on this side of the equation, I will now have sine to the negative first times n1 sine theta 1 all over n2. All right, so now I can plug in with units and I can get my answer. So we have here, I'll put it over here, so sine to the negative first. N1 has no units, we just need to plug in a number, so that is 1.46. Sine theta 1, that is going to be 28 degrees, all over N2, which is going to be just 1.00. That is equal to theta 2. So that will give us our first point here. Now I just need to plug in to the equation. I just need to plug this into my calculator and end up with my answer. So I'll have here 1.46 sine 28, then do arc sine of that answer. So if you look for the calculator for this, look for sine, press second, you have sine to the negative first, then you can plug in your answer here, and you should end up with an angle here, theta 2, because it's over 1, so you don't have to be plugging the 1 here. So theta 2 is going to be 43.3 degrees. It says for part B, and that would be the full 2 points. Your first point is showing the equation and the substitution there with units. And then your second point is getting the answer and having the proper units on there, which would be degrees for this answer. So this is the full work for 2 points, and part A was just 1 point getting the proper angle. So let's move into part C and D. All right, so part C, starting at point O, using a protractor and ruler, draw a refracted ray at the appropriate angle of refraction on the diagram in your answer booklet. So I'm just going to do it on the diagram here. You have a proper diagram in the answer booklet on the test day. And we're going to use the angle that we got in part B and just draw it out. So what I have here, looking at my protractor, again, I'm just going to count around 43 degrees away from my normal line. That is where the 90 degrees is here. So going to 100, that is 10. 110, that is 20. 120, that is 30 away from 90. 130, that is 40 away from 90. So we can start in this area over here. And now we just need 3 points away. So around this point here is going to be where my ray should line up with. I'll make it red actually, or blue. Blue's better. All right, so that's where the ray should essentially line up with. I'll try my best to do that since I don't have a ruler here. So we're just going to line this up here. And that should be then 43 degrees away, or 43.3 degrees. So just 43 degrees away from my normal line. That's where you want the angle of refraction to end up being. So now part D. Part D, you want to compare the frequency of the light in fused quartz to the frequency of the light in air. So this is just pretty much knowing this idea. When light goes from one medium to the other, the frequency is not going to change. What is going to change is, since my speed is changing, my wavelength will change, not my frequency. So all you're looking at is the frequency will stay the same. That's all you need to write down. So for this, the frequency will stay the same from one medium to the next. And that's all you need to put there. You can even just put the frequency won't change, and that would be an acceptable answer. Or you could say it will be the same, and that will also be an acceptable answer without even saying frequency. But try and say the frequency will stay the same so it's as clear as possible for your answer. All right, so I hope this review here was helpful. See you guys in class, and good luck in studying for the Regents.